Okay, it's time to analyze the stability of this explicit forward time centered space method for the diffusion equation we have just obtained, which is this one. Just remember that the alpha parameter here is d, which is the uh, conductivity times delta t over the square of delta x, and that's the stability analysis. It's quite straightforward. We have to use the Fourier method. We have to substitute the expression of the u function evaluated at n and j by this expression. If you are doing that, this is the result we have. Then after this, we have to simplify uh, all we can. For example, you can see the eta to j appears everywhere. We can simplify it. Then this exponential also appears everywhere. Then we can simplify. And then doing these simplifications, we can get that the eta is given by this expression. Again, the sum of these two exponentials is 2 times the cosine of k delta x. So we're getting to this expression, and now it's time to analyze if that satisfies the stability criteria, which basically says that the amplitude of theta has to be uh, lower equal than or equal than 1, and that's what we're going to do next. And for that, actually, we have to take into account that the limits of the cosine are both 1 or minus 1. So if the cosine is 1, then it's 0. Then you have the eta, it's 1, so it satisfies the stability criteria. And for those k values where on delta x values where the cosine is minus 1, then you have this is minus 2. And so the stability requirement is that this factor here has to be therefore lower than 1, so that when you are summing with 1, you are getting a eta that it's negative, but the absolute value becomes therefore lower or equal than 1. But for that, it's necessary this factor here to be lower equal than 1. So we are leading, therefore that's leading to us to the stability criterion here. This is the stability criterion for this explicit forward time centered space method for the diffusion equation. It can be stable, but you have to play with both time step and the space step in order the method to be stable. But here, so this stability criterion that you have here, this condition, it actually implies huge limitations on the calculation procedure. Because, for example, let's suppose that we want to analyze with great detail in space that make us to consider a very small step on space. So, but as delta t here it's related with the delta x squared, then delta t has to be smaller than delta x squared over 2 times the delta, 2 times d. So what we have is that delta t has to be much smaller, the time space has to be much smaller than delta x, because delta x is going with the square. What does it mean? That delta t has to be really, really small. So that huge number of time steps will be required until something interesting happens in the dynamics in your system. So we are forced to, in order to satisfy this stability criterion, we are forced to take very small time steps. So therefore, this, considering the stability criteria makes that the computational requirement can be really enormous. Therefore, that indicates that new methods are probably required. More flexible methods on the stability criteria are required in order to analyze that, probably because they are more efficient. This one, because this one, even though it's stable, it's not really efficient, especially as we have seen here, if we have to analyze with great detail in space.